SwayamPrabha. Digital India. Educated India.
Hello everyone. Welcome to yet another session of our NPTEL on Nonlinear and Adaptive Control. I am Shrikant Sukumar from Systems and Control, IIT Bombay. So we are in this very last week of this course on Nonlinear Adaptive Control, and we are talking about some exciting things. And I hope you found the course in general as a rather interesting course. So right now we are going into slightly more, say, advanced and research topics, and we have been discussing about learning. So we started the week by trying to create a chronology of how things evolved in adaptive control, and parallelly in stochastic and discrete systems in the form of self-tuning regulators. And also another parallel in the form of learning classification kind of problems. So I do hope that you, sort of are relatively convinced that whatever algorithms that you've learned through the curriculum will help you drive autonomous systems such as what you see in the background. So, um, so in this paper that we were looking at a very specific, um, learning setting, yeah, which is now a very popular setting, and that is the one on deep learning. So deep learning is essentially um, uh, learning algorithms that make use of deep neural networks, that is multi-layer neural networks, and that's the sort of application that we are looking at here. One of the uh, sort of differences from what you typically are used to in learning algorithms is that here we have everything to be online. That is, you're doing learning also in real time. So we of course established a parallel of deep learning or neural networks with parameter learning, right? So essentially that's what it is, because you have weights and then you're trying to learn some weights of the different layers on the neural network. So we did establish that parallel, and the difference here lies in that we are trying to do the learning online, that is real-time learning and control simultaneously, right? So we talked a little bit about where the literature is, right, in the beginning, and we also sort of try to understand that standard learning rules may not do a great job, and so the this article talks about some modifications to the learning rules, right? Now, um, we also then, of course, discussed a little bit of the background, right? Let's see. I want to see where I've marked these. Unfortunately, it does not look like I marked the lecture. Just a second. I think the first lecture, of course, started from the this paper here. So I think that's fine. That's marked in this paper. Right. So let's see where we were. Okay. I need to find it. Okay. Right. Just give me a second. All right. Not here either. There's the STR. I just want to find where I marked lecture number 12.2. Yes, that's here in the discrete and deterministic systems. And I believe we started, I'm going to mark it here as lecture and Let's see. Now this is fine. So this is, yeah, this is all of lecture 12.2, I believe. Yeah, yeah. I believe this is all of lecture 12.2. Yes, yes, this is fine. All right. So we do have all the lectures marked. My apologies. So then we started looking a little bit at the background of what is the problem setup. Pretty standard in most articles that you read. Here we talk about the type of norms on matrices and signals and vectors. Then we do the most important definition, which is that of how the neural network looks, which is with one input and one output layer, or you can, and then one hidden layer in between. Right. So this is how you have the three-layer neural network structure. So you have the inputs going in, and then they're scaled by some weights and an offset. Then you get a summation over them. And that's the second layer where you have this activation function, right? And then you have sort of the connection with the third layer, which is via this weight wij and the theta wi offsets. Yeah. So the aim is, of course, for the neural network to identify all these quantities. Yeah. And if you do, then you have a very clear relation between functional relationship between x and y, which is the input and the output. Yeah. Don't think of these inputs and outputs as a control, etc. This is a more general setting. All right. So we also saw that there are different possible choices of these activation functions. They can be sigmoidal, hyperbolic, tangent, or radial basis functions, right? And with some sort of flexibility in terms of how we choose, how we define our x and v and w and so on, we can account for both the weights and the offsets in this sort of a structure, which is this nonlinear regressor parameter form. Why do I say it's nonlinear? Is because you have this, w and also a v here. So this is what makes it nonlinear, because both w and v here are unknowns, right? So usually you would probably just have something like this in a regressor parameter form. Okay, but here you have first two different unknowns, and then you also have this activation function, which is also potentially nonlinear. Right? So um, then, of course, we talked about what it means for you know uh, something, uh, some function to be in the functional range of a neural network, and that was defined using this kind of an expression. That is, if you have the neural network, it gives you something like this. And then if you have a small epsilon offset from the true value of the function, then it's somehow in the functional range, right? And there are some nice results for specific cases of sigma, right? We were talking about these activation functions, and for some specific cases of sigma, you do have results which say that the functional range of the neural network is dense in the set of continuous functions. What we'll try to interpret this result of course. First of all, there is the uh, term squashing function. So, what is a squashing function? Uh, so basically, it's defined here. A squashing function is a bounded, measurable, non-decreasing function from the real numbers onto 0, 1. All right. So basically, this kind of function includes the step function, the ramp function, sigmoid function, etc. Right. So squashing functions, there are other relatively large class of functions. Right. So for these kind of activation functions in your neural network, what this theorem claims is that the functional range of the neural network is dense in continuous. So what does it mean? This statement, yeah, for those who have not seen analysis courses, essentially means that almost almost any continuous function can be approximated via this neural network. Okay. So this is a very specific neural network, by the way. It's exactly a 3-layer neural network. So one input, one output, and one hidden layer, right? So with this specific neural network, you have a result which says that uh, you can approximate almost any continuous function quite well with this neural network, right? So this is what it means. Um, so of course the dense is in terms of the supremum norm. So this is the whole idea of how you define dense. In fact, what the authors state here is that the last layer threshold values, that is the offsets, were not even required. Yeah, so the last layer thresholds were not needed for this result. So you don't even need the last layer thresholds for you to have a good approximation. Right? So of course, how to select these sigma and then choosing this N2 and for a particular set S are of course topics of research. So then there is this section on stability and passivity, which I'm going to skip for now. For now, I'm going to skip it. Yeah, if I do see the need, I will get back to it. Yeah, we have not discussed passivity, which is a very standard notion for nonlinear control. And if you have a system which is passive, designing controllers becomes sufficiently easy. This is this is usually covered in a more detailed nonlinear control course, yeah, which we don't aspire to be. We are more of a nonlinear adaptive control course. All right, so we will skip this for now, and we'll see if we need it later on. We will talk about it maybe in passing. Yeah. So then in this next section, the authors are starting to look at. Oh, by the way, I was supposed to start to mark the lectures. So I'm going to mark it here. Lecture 12.3. All right. So the third lecture of our last week. So in this section C, the authors start to look at the robotic arm dynamics. Yeah. Why? Because this is the application that the authors are focusing on. Yeah? I mean, if you focus on another application, of course, you can write the dynamics for that in a particular form. So this is the standard form for robot dynamics. It's called the Euler-Lagrange form. So the Euler EL equations, very standard to call them EL equations. Here, this is a structure which holds for almost any n-link robotic manipulator, right? So it is general enough, right? If you have an n-link robotic manipulator, you can use this. And this is written, these equations are written in what is called joint space coordinates. Yeah. So if you have any, I mean, I usually make this picture. I'll try to make this picture here for you folks. So if you have any sort of axis, say, right, and then you have a one joint here, right, then you have another joint here, and then you have another axis here, sorry, another sort of link here, joint. So this is say joint 1, okay, and this is say joint 1, this is link 1, joint 2, link 2, and then of course you can mark it, right? So now if you look at some coordinate system, say this is a 0 0, this point, then this coordinate in the world frame is usually has some coordinates in say 2-dimensional frame xy if it's a planar manipulator. If it's not a planar manipulator, then it will have all 3 coordinates. But let's keep things simple and say it's a planar manipulator. And so these are the coordinates in the world frame. But then there is another way to specify these coordinates. So this is, let's see, if you look at this angle, this is say Q1, and you look at this angle, this is say Q2. Yeah, so there are two ways to look at robot dynamics, or two ways to write the robot dynamics model. One is in the joint frame with these Q1s and Q2s, and another is in the world frame, which is with this X and Y. You see that both have equal number in this case. In this particular case, the number of joint coordinates and number of world coordinates are the same, but that is not necessarily true, right? Because I could have 20 joints in a two-dimensional frame, so I have a lot of redundancy. Yeah. Then of course there is many more joint coordinates than there are world coordinates. So and of course there is a forward and inverse kinematics. For those who have seen robotics, there is forward kinematics to move from the joint coordinates to the world coordinates. So that's again something standard. Joint to world is the forward kinematics, and the world to the joint is inverse kinematics. Yeah. So you have these kinematics, which means that it's just a relationship between the joint coordinates and the world coordinates, and vice versa. So that is what is your kinematics equation. So now what these authors are doing, they are in this particular problem, is they're writing the everything in the joint coordinates. So that's why you have these Q. Yeah, these are joint coordinates, or they're also in Euler-Lagrange dynamical notions called generalized coordinates. Why are they generalized coordinates? Because they could represent angle or also linear motion. Because you could have joints which are just lengthening or shortening. Right? So you could have linear actuators also, or you could have angular actuators also in a robot. Right? So this Q could represent both length and angle. Right? So that's why Q is also called generalized coordinates. Yeah. But most important to remember is that it is in the joint frame. Yeah, it is not in the world frame. So then you have this M, which is your inertia matrix. Right? So M is the inertia matrix. It is a function of your Q, which is the joint coordinates. Then you have Vm, which is the Coriolis and centripetal matrix, which is a function of both your Q and Q dot. Then you have GQ, which is usually the gravity matrix, and GQ is the gravity vector. The gravity, sorry, not the matrix, but the gravity vector. And finally, F, which depends on Q dot, is the friction, right? Then you have these terms tau and tau d. Tau d is basically any kind of external disturbance. Right? So any kind of external disturbance is sort of put into the tau d. We've already seen how disturbance gets into adaptive systems, so or any nonlinear system for that matter, and we usually assume that these are bounded, even though we may not know what the values are at each instant in time. And then you have tau, which is the actual torque that I can exert, right? So when you talk about this tau, for example, if you look at this manipulator, how would you apply this tau? You would assume there is a, there is usually a motor, yeah, M1, and there is another motor, M2, right? So you would have some motor here on this joint and another motor here on this joint, and this tau is essentially obtained by rotating the motor. Right? It could be whatever. I mean, you could have a servo drive, or you could have a, DC motor, whatever. I mean, you could have different kinds of motors, but the point is that's how you get the torque tau. All right, great. So once you understand how this robot works and how the model looks like, of course, we are not giving any structure for this M. Notice, if you have a specific robotic model, you will have to actually write the dynamics either with your Newtonian formulation or with the Lagrangian formulation or Hamiltonian formulation. But the point is, you will have to write the dynamics, and then once you put it in this structure, and you will be able to put it in this structure, uh, you will get the expressions for M, Vm, G, F, and so on. Yeah, excellent. Excellent. So, suppose how is the problem formulated? I mean, any control problem is formulated with some kind of a desired reference trajectory. And so this is, we are already used to this kind of a notion. All right. So this is how any control problem is formulated. So here you see that your desired trajectory is some qd of t, yeah, and this helps us define an error, which is the true value of the joint. Sorry, which is they have defined it in an opposite way. The desired value minus the actual value of the joint variable. All right. So if you have only angles, then the desired value of the angle minus the actual value of the angle. Right? Now, it is also well known in robotics to use this kind of a filtered tracking error, right, in order to do the analysis for this system. This is actually for you folks. This is essentially like a backstepping variable, right? Yeah, like a backstepping variable. Why? Because if you look at this dynamics, yeah, and if I did write it as, uh, this can be written as a double integrator sort of dynamics, right? So if I take Q1 as Q and Q2 as Q dot, right? Then what would be my dynamics? My dynamics would be Q1 dot is Q2 and Q2 dot or or M Q2 dot is equal to minus VM Q dot minus G Q minus F Q dot minus tau D 9 plus tau. Okay, so this is what would be my state space equations. And if you see, if I think of some kind of a backstepping type of algorithm to control design, because this is essentially a nonlinear double integrator, right? Some kind of a nonlinear double integrator. So if I want to use backstepping to design, then I would choose Q2 as some minus lambda Q1, right? Q2 desired would be some minus lambda Q1. And so R is like the backstepping error, right? So, I mean, of course, I'm writing everything in the error. If QD is 0, if QD was not there, then E is just Q. And forget the sign is irrelevant. If QD was not there, then E is just Q, right? So R becomes Q dot plus lambda Q, right? So that's what we said. We will choose Q2 as minus lambda Q1, right? And the backstepping error would be, right? So let me Q2 desired would be something like minus lambda Q1. If I was just looking at the stabilization problem, that is, I want to send Q1 and Q2 to 0. And the backstepping error would be what? Q2 plus lambda Q1. Yeah, and you see this is, and lambda is some positive definite matrix. This is exactly what you have here. Sorry, like a Q2 plus lambda Q1. Yeah, if there was no desired, if there is desired, it's the same, right? I mean, if I write it in terms of the desired variable, I will get something very similar, right? Because if I wrote this as E1 dot, E1 and E2, it will be E1 dot equal to E2 and ME2 dot will be some equation on the right hand side. Okay, I'll still get something very similar. It doesn't matter if it's tracking or stabilization. So this is like the backstepping, this is like a backstepping error variable. Yeah, it's very standard to use this in robotics. Why? It's obvious, right? Because it's a just a nonlinear double integrator, and for if you want to get some kind of strict Lyapunov function or get some good Lyapunov candidate, this is the what makes sense. Yeah. So of course, lambda is some positive definite symmetric matrix, right? I mean, you can of course have it as a scalar. Usually, you select it as some diagonal matrix. Right? You can either have a scalar or diagonal matrix. You can also have a full matrix, which is positive definite symmetric. Okay, it's just a design parameter. If you want. Okay? Now, if I take the derivative of r and I plug in from my equations here, right? It's not difficult to see that I will get this kind of an equation. It's not difficult to see that I'll get this kind of an equation, right? Because it should be evident to you that m r dot is equal to m e double plus uh, m lambda e dot, right? And m e double dot. So this is just m times e double dot. Sorry, this m e double dot is m q d double dot m q d double dot minus m q double dot. So minus m q double dot is this guy. Minus m q double dot is essentially vm q dot uh, vq vm q dot plus gq plus fq dot plus tau d minus tau plus m lambda e dot. All right. Okay. So this is this big thing that you get. All right. So uh, so what you do is you can write this. What you will do is you will write this whole thing. You want to write this whole thing as this guy. You want to write this whole thing as this guy. All right. And how do you do that? You simply you add and subtract minus VMR, right? And you just add and subtract minus VMR, and then you combine it with this guy. Right? So what do you have? You will have this. So this F is essentially to encapsulate all the remaining terms. So you have these two terms here, right? Then you have from here and from here, you have these guys. Then you have this term, here. Then you have this FQ dot coming from here. Okay. And of course, we have retained the the tau d and tau have been retained as it is, right? So I just need to check the sign. I think there is some sign issue here, or did I miss the sign thing? Somehow the sign seems off, right? If I take mr dot, I have me double dot minus me double dot plus m lambda e dot, which is fine. And so from me double dot, I have mqd double dot minus mq double dot minus mq double dot. I see. So I think I messed up the sign. So this has to be, all of this is with a plus. All of this actually has a plus sign. Right? So now it's okay. This is fine. All of this has a plus sign on it. So this is all fine. So then I have tau d minus tau. All right. So this F is what encapsulates this kind of a nonlinear robot function. So why do we call it a nonlinear robot function? Is because this is what sort of encapsulates the dynamics of the robot. Of course, there is also VM, but we are not going to worry about that term. This is what encapsulates what the dynamics looks like, right? So and this is this fx, yeah, where of course we have chosen x to include all these quantities, e dot qd qd dot qd double dot, basically everything that shows up here. You have qd double dot uh, qd dot, yeah, e, and so on. So you have all the variables appearing here, and so it's a function of all these variables x. Yeah, so you have that's how you sort of put it. Yeah, of course, it's also a function of q, which is not written here, but then that is already inside e. Right? So that's fine too. Okay. So great. So this is the sort of simple, relatively simpler structure that we'll work with. We'll try to drive R to 0. We look at what that means in the subsequent session, right? So we'll look at what that means in the subsequent session. So essentially, what we have done today is we have sort of continuing our discussion on learning based or adaptive control based learning, and we are using it for a planar robotic manipulator. And so today we spent some time understanding the dynamics of the manipulator. And in the subsequent session, we hope to look at the control design part of the manipulator. So I hope you're enjoying our sessions, and I hope to see you again soon.